I'm from Macquarie University. I'm working with Devika Kamas, and today my talk going to be mostly about circumstellar disks around evolved binary stars. What are their properties? What is their structure? What we know and what insights we recently found for them from direct high-resolution imaging. I'm going to start with a more general overview and then go to some of the key findings of my PhD thesis, because, yeah, as Alex said, I'm in the final days, basically, of my PhD, so I'm going to submit pretty soon my thesis. Yeah, let it work, please. Awesome. But first, let me start with protoplanetary disk. They formed during the early stages of the host star life as residual gas and dust from the star formation condenses into a disk and also provides material for further planet formation. Protoplanetary disks surrounding both single and binary young stellar objects are pretty extensively studied in the recent decades, and observational studies showed that these disks do exhibit a various substructure, and here you see some snapshot images of direct high-resolution imaging data in mostly near-infrared for various protoplanetary disk systems. And as you can see, they come in all sorts of flavors and substructures. And while during this talk I'll be mostly focusing on the disks around evolved targets, I'll be coming back sometimes to protoplanetary disks to compare what we see for our evolved system and what we know for young stellar objects. So recently, research led by Devika Kamas, Hans van Winkel, and broad team of international collaborators shown that there is another phase of stellar evolution where the disk can also be formed. So while one of the companions in the binary system evolves through the asymptotic giant phase, it loses the majority of its envelope in the strong stellar wind. And in the case of the binary system, the gravitational influence of the companion will strip away some of the material from the outer layers of the evolved star and terminate the AGB evolution. This interaction and this mass transfer process will cause the formation of disk not just around the secondary companion, but also a disk around the whole binary system. So these systems are known as post-Asymptotic giant branch binary stars or post-AGB systems, and these are the targets I'll be mostly focusing on, and these are the targets I was studying for my PhD. I'm not going to talk in lots of details about the single star evolution, but just to note some main properties of single post-AGB stars. We are talking about low to intermediate mass star in fast transition between the AGB and planetary nebula stage. Post-AGB stars have low surface density, they also have low metallicities, and they exhibit a near-infrared excess in the spectral energy distribution, commonly attributed to the presence of dust around the star. So in case of a single star, this dust will form a nebula further on, but as I've already said, in the case of a binary system, this dust would be shaped into the disk. Here you can see the sketch of the typical post-AGB binary system. So we have a post-AGB star. Can I use a mouse? Okay. We have a post-AGB star, we have a main sequence companion, we have a stable circumbinary disk with gas and dust. We also have a much smaller disk around the main sequence companion, and we have a high-velocity bipolar outflows referred as jets launched somewhere from the position of the secondary companion. If we compare this system to a representation of the protoplanetary disk around the young stellar object, and here on the right you see the schematic from the Dillemond and Monnier paper from 2010, you see that the structure in general is very similar. However, the luminosity of post-AGB star is much higher, so the scale of the disk is different. So our disk in evolved system is located further away from the binary that it's common for the young star objects. So our research group at Macquarie University and also collaboration use various observational techniques in order to comprehensively study this complex system. Each observational data gives us information about some part of the system, and we need to combine all of this information in order to get a full view of the structure and all processes that are going on. Post-AGB stars and post-AGB binary stars were detected quite serendipitously through the presence of the near-infrared axis in the spectral energy distribution. And here on the right you see one of the examples of the acidity of binary post-AGB star, and as you can see so on the x-axis we have the wavelengths, and the y-axis we have the respective flux. And as you see, towards the longer wavelengths, the acidity of the target start to differ quite significantly from the modeled acidity of the single star. So this axis peaks in the near-infrared and is commonly attributed to the presence of dust disk, which with inner rim located at the dust sublimation radius. So such near-infrared excess is also observed for protoplanetary disks, and this was kind of the initial idea for the interpretation of this acidity. Also, high-resolution spectroscopy time series showed that for several post-AGB stars, variable absorption feature appear when you observe the system during the orbital period. So there is some change in the spectral absorption lines, for example, the H-alpha line. And when the Volta companion appears behind the secondary star, the continuum photons from the primary are absorbed by hydrogen atom in the outflows, or jets. And this appears as a specific shape of the line profile. So here in this image on the x-axis is the radial velocity, which is the radial velocity shift from the systematic velocity of the binary. And on the y-axis is the orbital phase of the system. And through recent studies of this H-alpha line time series and modeling, both in spatial kinematic modeling and also radio interferometric modeling, it was found that these jets have in general quite wide structure and velocity outflows up to hundreds of kilometers per second. They also showed that these jets are quite similar in terms of structure to jets found in young stellar objects. So, coming to spectroscopic observations, they allow us to study the binary orbital parameters through radial velocity monitoring. They also shown that there is some crystallization happening in the disk, and they also showed that there is some amorphous and crystalline silicates. And I'm not going to go into too much details of spectroscopic studies, but one of the very interesting features is the chemical depletion observed in the atmosphere of post-AGB stars. So if you look at this graph, on the x-axis is the condensation temperature for different elements observed in the post-AGB star, and on the y-axis is the abundance of this element. And as you can see, towards the higher condensation temperature, there is a quite significant decrease in the abundance of the elements. And this is commonly explained by the reaccretion of cleaned volatile gas from the disk back on the post-AGB star, while dust and refractory elements are staying in the disk. Now finally coming to the disk. So deep near-infrared interferometric observations are able to resolve the hot inner rim of the disk and some information about the dust in the disk midplane. And those studies showed that mostly the inner rim of the dusty disk is located on the dust sublimation radius. However, there is a subgroup of systems called transition disks where the dust inner rim is located much further away than it's supposed to be by the theoretical predictions. And it can be up to 7 times larger. And the presence of this large dust-free inner cavity in the disk It's not yet clear what is the mechanism responsible for it. It is also observed in protoplanetary disks, and this is where we kind of got the terminology. So we use the same terminology that is used for protoplanetary disks. However, it is yet to be fully explained. We know that quite often in protoplanetary disks, the presence of this cavity is explained by the presence of some pressure bump caused by large exoplanet or maybe substellar companion. Also, radio-interferometric observations assess the dust emission further from the star than with infrared interferometry. And these observations have shown the disk is mostly in Keplerian rotation. The disk size in general goes up to 1 second in angular dimension, and in astronomical units up to 500 astronomical units from the central star. And also the CO line observations showed that the general gas disk mass is around 10 to the minus 2 of the solar masses. So, advanced direct imaging instruments equipped with extreme adaptive optic provide access to the scattered light from the disk surface. And with these observations, we can study the morphology of the surface layers of the disk, and also we can study the properties of the dust grains on the surface. So here is, for example, one of the post-AGB systems observed in just scattered light, and for this system, the orientation of the disk is that the disk midplane is mostly blocking the direct light from the star, and this allows us to resolve the disk. However, it's not the case for all of the systems, obviously, and when the system is oriented differently, when the disk midplane is not blocking the star, it comes to the situation where we try to image the firefly next to the lighthouse. So we need to somehow block the light from the central star or suppress it in order to resolve the structure of the disk and study the disk itself. Unfortunately, due to typical small angular size, up to 1 arcsecond for disks around evolved stars, we cannot use chronographic masking because it blocks the whole scene, basically. So we need to find another way. And to do this, we rely on polarimetric imaging. Stellar light is mostly unpolarized, while light after scattering on the disk surface became polarized. So using the polarimetry, we can differentiate between direct stellar light and light from the disk, and in this way suppress the light from the star. So this is what my research is focusing on, and I use observations from the VLT sphere instrument to resolve the outer parts of the disk and resolve the structure on the disk surface, and also dust grain properties and composition for these disks as well. This instrument has 2 cameras, IRDIS and ZIMPL, and these 2 cameras allow you to do high-resolution polarimetric imaging in near-infrared and optical wavelengths. Here on the left, you can see the sketch, how the scattering of the stellar light is happening on the disk surface. And in general, scattering happens in 2 modes. So if the grain size is smaller than the observed wavelengths, it would be Rayleigh scattering. So the scattering would be isotropic in all directions, and the disk would be looking mostly uniform in brightness. But if the grain size is comparable to the wavelengths or larger, it would be Mie scattering, in which there is a much better efficiency for the forward scattering, so scattering towards the observer, than to all other directions. And using this feature, we can already differentiate what are the estimate of the grain size on the disk based just on the distribution of the disk brightness that we see. So, as I've already said, the stellar light is mostly unpolarized. However, after it scatters on the dust grain, it became linearly polarized. And this allows us to separate light that was reflected from the disk and light from the star, and suppress the light from the star. So if we are assuming that our disk is optically thick, it's not too highly inclined, so inclination is not really exceeding 60 or 70 degrees. And if we assume that it's single scattering on the disk surface, the orientation of polarization vector of the light would be azimuthal with respect to the central star. So in this way, we can differentiate between real physical signal from the disk and whatever happened to the light on the way from the system to observer. Because in the interstellar medium, you also have dust grains, and you also can have scattering and polarization of the light. However, in general, it would be randomly oriented, so we can kind of filter it out. So from the observations, we obtain components, Stokes components of the polarization vector. So here the I is unpolarized intensity, so it's just total light, which is fully dominated mostly by post-AGB star. Q and U are linearly polarized intensities, and V is circularly polarized light. Using the linearly polarized intensities, we can calculate the intensity that is azimuthally polarized and filter out everything else that we mostly assume to be noise or some interstellar polarization on the way. And for circularly polarized light, we also cannot differentiate what part of it coming from the disk and from some scattering, and what part is caused by interstellar medium. So basically, when we're looking on our data, we do the lower estimation of the polarized brightness of the disk, because we filter in the signal that we definitely know coming from the disk, and everything else we treat as noise or interstellar. So coming to the directly results of my thesis, first I'm going to present a little bit what are the targets we used in my PhD project and what was the methodology for it. So we use observations from both simple and NRDIS cameras of the sphere, and we perform the high resolution imaging and polarimetric observations. The target sample consists of 11 representative post-AGB systems that have a quite wide range of temperature, orbital period, inclination, and also range of chemical depletion efficiency and shape of spectral energy distribution. As I have already mentioned, recent interferometric studies showed that some post-AGB disks can be classified in two groups, with like full disks, where the dust inner rim is located on the theoretically predicted dust sublimation temperature, and also transition disk, where there is a large inner cavity. So in our data sample, we have two systems that are transition disks, so there is a large inner cavity, and other 9 systems are full disk models. So we also do comparison between what we see for them. Unfortunately for us, the typical distance to our targets is around 1 kiloparsec and more. So we're looking on pretty small size of the target with sphere data. So we're looking on the, something within few hundreds of milliarc-seconds from the central binary in sphere. And this region is quite significantly affected by the instrumental bias and instrumental polarization effects. So we have to be pretty careful what we take into account and how we reduce the data. Sphere instruments have a semi-developed data reduction pipeline, and we found that it was not really nicely working for barely resolved targets that we have. So one of the challenges in my PhD was to develop the proper data reduction and analysis routine that would allow us to, as accurate as possible and precise, get the polarimetric measurements for barely resolved targets and treat it carefully. I'm not going to go in all of the details for the data reduction, but here are the main steps that we do. And we perform the basic polarimetric differential imaging reduction using the available softwares. We then correct for the telescope polarization, which is also different for different orientation of the telescope. We select the frame, so we do the filtering of the data, selecting only the best part. We correct for the unresolved part of the disk, because for quite a lot of systems, the brightest innermost disk part can be resolved with sphere. And we perform the correction of polarimetric constellation effect, which is caused by the convolution with a point inspection during the observations. And finally, we define the statistically significant region of the image by comparing the alignment of the polarization vector for our data and also signal-to-noise ratio. So as I said, for some of the reduction steps, we use already existing pipelines. However, we modify them where necessary to fit our targets. Here is an illustration of the main reduction steps that we do with one of our targets. So these are simple camera data. And as you can see, the issues that we faced first was after the basic reduction with existing software, the image was kind of rotating during the time of observations, which is not supposed to be. So this was the bias coming from the telescope polarization that was changing during the observations because the orientation of telescope was changing. So we adapted slightly the SZ pipeline developed in the ETC Zurich to correct for that. We also correct for unresolved polarization because, as I said, we cannot resolve the whole disk. The inner rim of the disk with sphere is still unresolved. So we have to subtract some halo that this unresolved signal creates. So for most of the images, this innermost dark part of the disk is not really the cavity, is an observational bias because we subtract the unresolved halo in the images. And also to further correct the image, we perform the deconvolution with the observational point spread function. We have also developed a set of Python scripts to analyze the polarimetric imaging data in a consistent and precise manner for our targets. And I'm again not going to delve into all of the analysis steps, but in general, we first compare the polarimetric measurements in different apertures to find out whether unresolved polarization mostly coming from disk or it's mostly caused by in the stellar medium. We determine the disk orientation, we measure the polarized disk brightness, we calculate then profiles for the disk, both radial and along the disk surface, and then we go to the confirming the substructures that we see for these disks and combining observations from both IRDIS and simple camera, we perform multi-wavelengths analysis for our data. Here is a little bit of illustration for different data reduction steps. So on the top left is the defined statistically significant region that we do before the further deconvolution with point spread function. Then for the smallest resolved disk part, we fit an ellipse to define the disk orientation. Then using the disk orientation, position, angle, and inclination, we plot the brightness profiles, and then we go into the confirmation of the disk morphology and also the measurements of the total disk brightness to later compare it within the sample and with targets from young solar objects, for example. So here are already reduced linearly polarized images for 8 post-AGB systems that were observed in near-infrared with the IRDIS camera. And as you can see, they show various morphologies and complex structure with outflows. Yeah, not working. With outflows, arc structures, rings, and also scattering from the other side of the disk as well. As you may remember, I've said earlier that we have 2 targets that are transition disks, and when you compare them to the other targets that are full disk system and don't have the large inner cavity, you see that from scatterlight observations, they already look more complex and asymmetric compared to full disks. So there is definitely some intrinsic process that's going on and changes the shape of the disk, and yeah, we need to further investigate what is going on there. We also find that some systems exhibit bright substructures, while others lack of the more extended disk structure. So our findings indicate that there is a correlation between the presence of the more extended substructures in the disk and the proxy of initial metallicity for the star. So from theoretical modeling, we know that the dust production during the AGB phase of the star is correlated with the metallicity of the star. So it would be more efficient, the star is more efficient in the dust production if the metallicity is higher. So potentially this can be the cause for these systems as well, as we don't see so extended structure for disks with lower proxy of initial metallicity. We were also able to perform the direct measurement of the disk scale height for two of the targets. So for the left one, we see two rings, and the outer ring is visibly shifted from the position of the central binary. And this shift is a projectional effect for the flat disk surface when you have an inclined disk. So using this shift, we can measure the scale height of the secondary ring above the midplane. And for the system on the right, we directly resolve the midplane of the disk, so we can measure it directly. This parameter is quite important for the further modeling of the system, as comparing with other observations, for example, ALMA, continuum delta, we can estimate the dust settling parameter. So previous results were based on monochromatic observations, and now let's shift to combining observations in near-infrared with observation in optical with another camera of sphere. So here are results of optical V and I band. So in top row we have V band, and on the bottom row we have I band for 6 targets. 3 of these targets were also observed in near-infrared. So the second one, fourth, and the last one. And as you can see, they all show quite also interesting substructures and various morphology, but most of them appear quite similar in different wavelengths. At least we find that orientation of the disk is quite consistent when we compare the optical and near-infrared data. However, for some of the targets, it is showing some interesting change in morphology. So now let's focus just on one target, which is IRS-08544431, and for shorting, I would just call it IRS-8. This target is showing more elliptic disk structure when we observe it with shorter wavelengths. The infrared observations for this target showed that the dust inner rim is ruled by dust sublimation radius and dust sublimation physics, so it is larger than the binary truncation radius. Therefore, we can assume that the disk itself should be circular, and any change in the appearance of the disk in terms of how elliptical it is are coming from the projectional effects. So, with disk being more elliptic towards shorter wavelengths, we can estimate the inclination of the disk, and disk appear to be more inclined towards shorter wavelengths. Both difference in inclination and also extension of the disk and of the resolved disk structure with wavelengths, combined with the fact that dust opacity decreases with wavelengths, lead us to suggestions that potentially maybe the innermost part of the disk is warped. This effect is now observed for protoplanetary disks, and it can be caused by misalignment of the binary orbit and the disk midplane. It can also be caused by the presence of planet or some other physics and interaction of the disk and the central binary. However, it is very interesting that we see the signs of warping and not just the smooth disk structure for this target. We also investigated the brightness distribution along the disk surface of this target, and we found that one side of the disk appears brighter than the other one. And this is the sign of presence of forward scattering peak, and is consistent with modeling results for aggregates of dust with size of at least 1 micron instead of much smaller dust grains on the disk surface. So we estimate that the northern disk part is actually like inclined towards the observer, and that on the surface we have mostly porous dust aggregates as dominant dust species. Just for comparison, for the other system, for human, we also have slight difference in different wavelengths, and in H-band we see this like an outflows and arcs, which not present in the shorter wavelengths, but the difference is not so obvious and so significant as we have for RSO target. And for short target HR 4049, the size of the disk and the inclination is absolutely same in all wavelengths. So, as I have mentioned somewhere in the beginning, RPUP is quite interesting target, which is luckily for us oriented. So we again observed it with polarimetric differential imaging. So as you can see on the left, there are polarized light images, and on the right is just direct imaging. So it's light that was just scattered, but we haven't filtered out yet only polarized intensity from the disk. And as you see, the lower part of the disk appears brighter. So this is this two-ball-like, arc-like structure that we see is two surfaces of the disk. So you have two flat disk surfaces, and you see the polarization and scattering from both disk sides. And the lower surface is oriented to us, so light that is scattered on it goes directly to the observer. And the upper one oriented from us, so the light has to be scattered and then go through the optically seen part of the disk to get to the observer. Having both the scattered light images and polarized light, we were able to directly measure the maximum polarization efficiency for this target and for dust on the surface, and we found it to be around 70% in the V band and 55% in the I band. And this is important for further modeling what dust composition is consistent with this efficiency of polarization and also with the distribution of the brightness that we have for these targets. Now coming to more comparison between post-AGB disks and disks around young stellar objects, we are measuring the disk brightness relative to the brightness of the central star. So then we can directly compare the brightness of our disks to brightness of protoplanetary disks in polarized intensity. And here on the left is our sample, and on the right we have sample of T Tauri and Herbig stars from paper MATISSE 2023. And as you can see, our targets are among the brightest protoplanetary disks. So the efficiency of polarization is definitely not lower for our disks than it is for protoplanetary systems. And on this side, we compare the color index. So the color index can be between, if it's less than -0.5, the disk is assumed to be blue, so the brightness of the disk decreases with wavelengths. If it's between 0.5 minus to plus 0.5, it appears to be gray, and if it's higher, then it's red. So for the red disk, you have the disk is brighter towards longer wavelengths. And on the left side, it's post-AGB sample, and on the right side is again the same sample of T Tauri and Herbig stars. And as you can see, for our disks, they mostly show gray or slightly blue color, which is consistent again with dust aggregates instead of single monomers. And for protoplanetary disks, they also commonly show the gray color, even though sometimes they go slightly more towards red. Now on this slide, you can see how our high-resolution direct imaging data complement the interferometric observations. So on the left is a combination of the V, I, and H band observations with sphere for the RSO target, and on the right is reconstruction of the dust inner rim of the same disk with near-infrared interferometric observations. So to sum up our comparison between post-AGB disks and protoplanetary disks, here is a table with different parameters, observational parameters for the systems. And as you can see, despite different formation nature, different lifetime, and also in general quite smaller disk mass for circumbinary disks around evolved stars, as observational parameters, they do appear very similar. So while we cannot say whether protoplanetary disks and post-AGB disks can both form planets or is there any planet formation, the post-AGB disks do appear very similar, and it is an extremely interesting target to study the extreme environments for disk evolution, disk binary interaction, and also dust processing that is obviously happening in these systems. And also this is like a comparison that the structures that we see for protoplanetary disks, which are the light from the other side of the disk, some outflows and rings, we also have it for the post-AGB circumbinary disks. Even though the distances to the target is much larger and the resolution is not so great, comparing to protoplanetary disks that are much closer, but we still have very similar structure and morphology in the surface of the post-AGB disks. And here is also a bit of a gallery of different disks that we observed for post-AGB targets and different features that they show. So we have disks that are just clearly elliptical and nothing else is going on around. We have some rings and arcs. We have also resolved backside surfaces for 2 targets, and we have some disks that are just asymmetric and more complex than others. So, in conclusion, we have achieved for the first time direct imaging and polarimetry of disks around post-AGB binaries, and our findings highlight the significance of post-AGB binary systems in understanding the disk formation process, disk binary evolution, and interaction in disk dynamics across HR diagrams. So we cannot just look on protoplanetary disk, we need to extend the sample and look on more targets around evolved stars to fully understand the physics of the disk formation and evolution. So by combining our results with studies of chemical properties and interferometric observations and radio interferometric observations, we finally start to piece together all information that we have for these targets and get a more full view of what is going on there. And talking about the future work, we currently extending the samples that we have. So we have observed only 11 targets, with only 2 being transition disk systems. Now we have a successful sphere proposal that is currently under observation to get a more transition disk systems and get a larger sample to study the morphology and dust properties. And we also look forward to use both already existing telescopes like Subaru Extreme Adaptive Optics. There is an upcoming upgrade for Sphere with a better sensitivity and contrast, so we're looking forward to that. And also for the upcoming great big instruments like MATISSE and ELT. So while I'm really happy to take your questions, I would also like you to take out your smartphones, just scan the QR code, and keeping in mind all of the similarities that we have for comparison protoplanetary disks and disks around evolved stars like post-AGB binaries. Do you think it is likely that these disks can also be the place of the planet formation? Or do you think it can only be possible for the young stars? Thank you very much.
At the very start, you mentioned that the main sequence companion can have a small disk around it as well. What stops that disk being blown away by the light of the star?
We detect that disk. First of all, we see the outflows from the position of the companion that is from the modeling most likely to be driven by stellar wind and wind from the accretion disk around the companion. So we have that information. We also see that disk in some of the interferometric observations. I'm not so sure what stops it from being blown away, but we definitely have observational evidence that it is there and it's definitely present there. And for long enough to launch the jet.
Yeah, question about the binary stars. So do you know much about the companion? Are you sure they're main sequence stars?
Yeah, so from first of all, we have the outflow velocity for the jet. that is mostly defined by the gravity of the companion, and those velocities are consistent with main sequence companion, not a wave 12, for example. We also have orbital periods and orbital parameters for, we have 85 post-AGB binaries detected so far in the galaxy, and for most of them we have all orbital parameters, and they're also consistent with like more main sequence companion. It is also interesting that for post-AGBs, the periods are behind hundreds to thousands of days, which is in between of theoretically predicted for systems that are or undergo the common envelope or have more wider orbits. So it's also have to be explained how these targets land up in this particular binary orbital periods and not separated into like bimodal distribution that is expected for them.
So first a comment on Daisy question. Isn't, in a sense, the jet evidence is exactly what's happening? The disk around the main sequence companion is being blown away, just constantly being
refed by the accretion from the larger disk, or from the binary,
On your final question, do we have evidence that this has happened in the form of the planets around a neutron star?
We have systems like
system. Isn't that telling us this is exactly what happened?
So we have binary systems like white dwarf binary systems where we have planets, and it's not clear whether the planets have survived the interaction between the binary companions or these planets were formed later on. And there are systems like Anensor, which is dwarf binary systems with confirmed planets. I think it's 2 or 3 confirmed planets for that system. And from theoretical modeling, it is more likely that they were formed later than the star itself. So we know it happens. We don't know what is the place, what is the stage. So this post-AGB binary disks is looking to be very promising exact stage of evolution where it can happen.
So first of all, great talk, first of all. I was wondering what fraction of post-AGB stars have disks? Is it like all of them, or is it a very small fraction?
Well, all binary system confirmed so far have disks. Single not, so there is a more between how many binaries compared to single stars do we have. And in Galaxy we have like 85 binary systems. I know that in small and large Magellanic Cloud, let me think, out of like 200-ish post-AGB candidates, around, I'm not so sure with like exact number, but around half of them or sort of them are definitely binary systems. I just don't have this number on top of my head.
Rephrase the question. So if you have, they all have infrared excess? Some of the infrared excess is not from a disk?
Some, there is a different shape of the SED for the shell targets and for the disk targets. So based on the shape of the SED, we can first differentiate whether it should be a binary or it should be a single star, and then we can confirm it with radial velocity monitoring, whether it's like definitely binary system. So for the stable disk, the near-infrared peak, like the peak of the axis would be near-infrared or a little bit further, and it would be like 2 separate peaks, but for the shell it would be like more continuous because it would be like more stellar winds and emission from that dust.
So all the binaries have disks, and about half of them are binaries.
Something like that, Not exactly sure about the half, don't have the number on top of my head, but
And the second question was, you mentioned like a warp. So if this thing is produced by the wind from a star, presumably it's been shaped by the binary companion. So what's going to warp it?
So the system for the RS-8 case that I was showing for this like presence of warp that we see always suggests that it's a warp that causes this structure observed in scattered light. From interferometry and from the location of the inner rim of the disk that we cannot resolve with sphere, it is smaller. It is further than dust truncation radius. So the disk, the inner rim of the disk, and further out shouldn't be shaped by the binary itself so much, so it shouldn't cause like warp. Maybe it's something else, but it also can be if the binary orbit is significantly misaligned with the midplane of the disk, because I found some modeling papers for protoplanetary disks
So
But
that's
like-
the question. Like, so
Yeah.
if the binary was the thing which helped form the disk,
Mm-hmm.
how can the disk be misaligned?
That's true, and like we don't have the answer what would be causing the warp yet. I think we do need to do some modeling and more theoretical understanding what, but we have observational evidence that potentially there is a warp in that system.
Yeah, planets and binaries which are misaligned with their accompanying stars. It's the same history in some sense.
So you got multiple disk formation episodes, you have
Yeah.
infall events, but here you've only got one outflow event, and the binary shapes it into a disk.
But it's also recreation back on the binary. Would it be helping to do the misalignment between the orbit and the disk midplane?
But also in these systems, the depletion pattern that you see on the star has something to do with the disk and the binary system constantly.
Yeah, so we have confirmations that they're constantly in the connection, yeah.
Yeah, and the warp itself, I mean, it was more, I think we see that as the signatures that we're extrapolating from the young star, and I guess some amount of theoretical modeling on if there is a substellar companion or a planetary companion, can that somehow be causing that?
Be the
Is
reason,
is
yeah.
the science question. Because if you look at the depletion that you see on the majority of the binary post-AGB stars, there has to be something that creates a dust trap, and that the explanation for that so far is there's a planet that's carving that dust trap. Well, we haven't, that's a so far explanation, but it's something to probe there.
Yeah, so we have different observational evidences of potential planet presence in the disk. We cannot detect it like visually or detected it obviously through the observations, but we have indirect confirmation or some evidences of potentially a planet being formed or being there in the disk.
I mean, I think for these systems, the chances of actually detecting the planet is very small because
Yeah.
the star is so bright compared to the planet you're expecting to find. So signatures are your best bet. I mean, so the stronger you can cement with signatures, that will actually be your indication of the planet and the modeling, of course. But
Yeah,
imaging the planet like you do in young stars, possibly with MATISSE, but even then I don't think so. It'll mostly be pressure bumps and cavities or spirals.
Yeah, so the resolution even with upcoming instruments in the next few decades wouldn't be enough to resolve the planet itself, but from the modeling we can link the indirect observations and indirect evidences. If we can say that there is only like the planet presence or planet formation is the most probable cause of all of these effects, it would be really great, and then we can kind of step on it.
And there's some times left time. So first the usual question, do you have any triple systems potentially?
Haven't found yet. So we don't have any observations for the triple system. It would be really interesting to look and study. Maybe for some of the systems there is some like substar companion or something, but there is no observations yet. We haven't confirmed any of that.
It's a bit of follow-up on Daniel's questions. If you just randomly pick up a star or a binary system, what are the odds for it to harbor a planet, second generation planet?
It's a more statistical, not so sure with exact number or what would be the odds for it to really harbor the planet. I think the approach that we take with this disk, we started with just looking, okay, what does it look like? Yeah, these are very interesting targets. And then while we were getting more and more observations, we found that they are so similar to protoplanetary disks that we started to think, okay, we have all these evidences, maybe there is a planet formation. But I don't think I have any number in my head how probable for the some out of blue binary would have the second generation planet formation.
Can I just add to that? I mean, I think we've classified our disks into subsets, so those that have possibly larger cavities and those that are a little bit more smaller cavities. So we call them transition disks and full disks. So I think if you have to be really conservative, you might say because these stars have larger cavities in their disks and, their inner rings are much further away than the binary, they may be the population. So that, I think the percentage there is
The percentage would be
10% of the systems. But then again, we also find the full disks are very depleted. They also have jets.
And also the warp is actually in full disk systems, so.
But many of our observational programs, just to make sure it's like a pilot program, they're always targeting to start off with the transition disks to kind of proof of concept, and then going on to the full disk. So I'd say you can sort of give like a 10%.
10%, yeah.
But yeah. That doesn't go to say that the others may not, if that helps. Yeah.
So I know this is a question that hasn't even been fully answered for protoplanetary disks yet, but if there's planet formation going on in these disks, what do you think kicks it off? Like, do you think it's disk fragmentation from gravitational instabilities or something else?
Because we were focusing more on whether it is possible to form actual planets, I wouldn't say we were like looking what can cause, but I think it can be some gravitational instability caused by the binary, like during the formation of the disk, that would further like induce a pressure bump and cause the initial start of the dust coagulation and formation in something bigger, and that this formation of some proto-planet core would further cause the pressure bump in the disk and the depletion, for example, more efficient for some systems and separation between gas and dust. So it's as an option, but yeah, I wouldn't say we really looked into my details what would cause it. So it's also the question we would like to address in the future.
Question? Probably missed your explanation, but you have a method to measure the scale height of the disk by looking at two concentric rings. Why do we have rings and not a continuous distribution?
So with sphere, we look on the light that is scattered on the surface. So the explanation of the shadows or like ring structure, it can be two options. Whether there is lack of dust in between these rings, so there is some pressure bumps that causes less dust in between of them, or it can be some shadowing. So because we look just on the surface. So we need, for example, some ALMA continuum data and polarimetry, for example, from ALMA to investigate the structure from the mid-plane going up of the disk and differentiate between whether there is actual pressure bumps that cause the formation of rings or whether there is just a shadow caused by like a bit thicker part of the disk and then it's thinner and then it goes on again.